All right, so what do you guys want to do today? Do you have any questions for the reviewing or getting ready for your tests on Monday, a week Monday? Or you guys got, or we should just continue, cover new material? All right. So long time ago, we were doing recursion, and pretty sure we got to through merge sort. So what we'll do now is quick sort. All right, so back in the 70s, sorting fast was what computers were really working on doing because they were slow, and this was a faster algorithm. And the reason it was faster than merge sort is because merge sort requires you to copy the data out and then kind of merge it back in, while quick sort all does in place just by swapping items quickly. So what's the algorithm is, again, we're going to divide the set into two lists, but this time what we're going to do is we're going to choose a random pivot, and then you go through it and you put everybody who's smaller or equal to the pivot on one side and greater or equal to it on the other side. And then you recursively sort the one half and recursively sort the other half. And then the two can just be put back together. Everybody get the algorithm? And so here's kind of a tracing it out. I made this before the days of PowerPoint. Here's the input, and we choose a pivot 25, and so these are the numbers smaller than 25. These are a number bigger than 25, and then we recurse this. Everybody kind of understand this picture, right? So I call it on this list, and then this friend partitions based on 10, and then this friend partitions based on 9, and all right. So which element should we let the pivot be? And one idea is just use whatever element happens to be in the first cell of the data. And the problem is that if the data is sorted, then when you do the pivot, you're not doing a very good partition of it in half, right? We're wanting to cut the list of data in half, and this doesn't do it. It's really only pulling off one number, right? So then it becomes more like you're doing insertion sort or selection sort, and the running time is n squared, right? So in fact, if the data is random and you did this, it would work quickly. But if you sorted it and then you ran sort again on sorted data, it would do badly. All right, so here's the various, what's the best running time is every time you pivot, you cut the list in half. And then, well, we haven't done recurrence relations yet. We'll do them next soon, but it comes out to n log n is the running time. In the worst case, you just peel off one, small amount, and then the running time is n squared. And you can kind of argue that it's more likely it's not going to be half-half, but it's going to be something like the small side would be something like a third or a quarter, right? So, and then the running time is still n log n. So that motivates grabbing a random pivot. We haven't really done running time yet, but this sort of shows. This is the whole array, and then we split it into, a third. Let's say that we split it a third each time, right? So that splits a third. And how much work do we have to do on that top level, right? We have to look at every number and put it on one side or the other. And on the second level, well, one friend is looking at every number on the one side, and the other friend is looking at every number on the other side. So it's still every number gets looked at once. And at each level, every number gets looked at once, right? So the question is, how many levels do you need? And it's not a level side, because the side where you're going a third, third, third is going to stop sooner. But even this side that goes 2/3 is still, it's still the number of levels. It's going to be order log n. So the running time is still in log n. All right, people, okay? There's various code. Anybody want to go through code? Let's skip this problem.